I will check here if it's.
Yeah, machine learning and Professor. Está. Sit down, don't worry. No, acércate o como quieras. Y Oscar también, lo podemos sacar como...
Sí, los tres, ¿eh? Otra vez.
Gracias.
Bueno, vamos a empezar. Gracias.
Sí, por favor.
Yeah, it's live.
Estaré aquí, ¿vale? Pero si tengo que salir, I will be here. This is not anymore the logotype of the University of Malaga.
They changed.
Sorry.
No, they have changed the year.
So should I change it?
Yeah, because the other is perfect.
I can do.
It's the Picasso
Yeah.
beard, but Picasso was asking for some retribution.
Okay.
So perhaps if you access to University
Yes.
of Malaga logotype, it's fine, no?
Okay.
UMA logo. UMA.
Everything is pretty slow.
Yeah, you are screaming.
Yes.
But I don't know how to enter in this way. Ask for UMA logotype. Yeah. Yeah, but I don't know what is the...
It's on top.
This
¿Dónde
one?
está la... Yeah,
This
this
one?
is the new logotype. Yeah,
This one?
yeah, this is the full one.
Le pillan con la palomita.
Sí, pero ¿dónde se...? Oye, tómalo para denunciar que he perdido todo por internet. ¿Hay alguna forma? Sí, ya también salimos. Así como les he dicho que los iba a probar a todos. Ay, Dios mío. Faltan 5 minutos todavía. ¿Ya está? Sí. No, pero estos son los de
pero los otros también. O sea, lo que hacer es una pizarra y le he dicho que
y que no viene, callado.
eso lo he dicho.
No, pero yo les dije que están haciendo otro trabajo por eso, pero...
Osvaldo, is it good that way?
Perfect.
Maybe a little bit larger. Huh?
And do you think that machine learning is able to identify that the horizontal gain in your logotype?
I
They
don't
use
know.
that this is a-
I don't know. I don't know.
Yeah, they're coming.
I know.
Yeah, I will just recommend you just in case you.
Yes. So, but you have the stream open, so you will see. Yeah, okay. Yes?
I do it very well. Well, good morning, thanks for coming. Probably you know Professor Ulrich Bodenhofer from the University of Linz. He was here the last year, 1 year ago, more or less.
Yes, Mark.
Yeah, 1 year ago with a similar seminar on machine learning, but of course updated to include deep learning. You well know also that Ulrich team is one of the teams in deep learning that are in the wave. Okay, so Ulrich really is a really good conference.
I hope so.
Yeah, you know. I don't need. I would like an interactive seminar. Of course, Ulrich will make the decision, but please participate, ask whenever you want, whatever you need. This seminar is being transmitted by the streaming, no? And at the end, perhaps we will have a questionnaire to evaluate Ulrich and to decide if we are going to pay his stay here. Okay? So let's enjoy it with Ulrich. Thank you.
Okay, thank you very much, Osvaldo. Good morning, everybody. It's a pleasure for me to be again in Malaga. So welcome and thanks for coming. I really love being here. I stopped counting it my 12th or 13th time around, but I'm not absolutely sure. I will not stop coming until you explicitly tell me. Okay, so welcome everybody. Thanks for coming. It's a pleasure for me to be here. I also greet everybody on the live stream because I've been told that my doubtable performance is being transmitted to the World Wide Web today. I don't know how many people are listening, but anyway, okay, so welcome and good morning. Osvaldo already introduced me, so there is not a great need to say my name again. I just wanted you to tell you that if you have any questions, not only today, also later, you can contact me anytime and ask me and get in touch with me. I'm always open to questions. Okay, so what is this about? This is about machine learning with a greater emphasis on deep learning than last year. Okay, that's exactly what Osvaldo suggested me to do here, and that's exactly what I will try to do. So I will provide you with the basics of machine learning because you can't do deep learning without knowing at least what supervised machine learning is. We'll also talk about some simple methods and other methods, like neural networks, like support vector machines and random forests. But I will try to keep these things a little bit shorter than last year, in order to put more emphasis on neural networks and deep learning. I'll provide a very crude overview of unsupervised machine learning, for sure not today. So that's for tomorrow. And I also try to provide you with some practical things. Okay, so let's get it on. I just wanted you to know that all of what you see here and all about what I'm talking today is available online. I put the slides and some sample code online. So this is the URL where you can find this. From there you can download everything. It's not the latest version. I just changed to the new logo of your university. So the version that you can find online still shows the old logo. What did you say? The mustache of Picasso or something like that?
Yeah, it's the Picasso thing.
Yeah. Okay. Anyway, that will be the only difference, I promise. And once I'm finished today, I will also update this. Okay. So moreover, I will show you a few practical things tomorrow. And I will use the scientific computing platform R for this purpose. In case that this is new to you, don't be afraid. I don't think that it will really be a major problem, because the code is relatively self-explanatory, and I provide you with everything, plus even the code executed and the results. So I think it should be manageable to understand it, and also to run it yourself, to learn by doing. Of course, it takes a little bit longer to master R, but it's not about mastering R. It's just about getting your hands on something.
Okay. As additional information, Aloy is Reg from the University of Limstone, and next week we deploy a seminar on R coding now. Okay.
Yeah. Okay. That fits together perfectly.
We need to work together.
Yeah. Okay. Good. So I will now change to the other. Okay. So the world is full of problems, right? And you, as scientists, engineers, whatever, are studying to solve problems, right? But there are different kinds of problems, like finding solutions of a system of equations. It's a mathematical problem. Predict the trajectory of a bullet, or a space shuttle, or a rocket, or whatever, right? So that's physics, basically. If you want to diagnose whether a patient has a certain disease or not, or which disease a patient has, it's a medical problem. If you want to predict the outcome of an election, okay, seems to be a really difficult problem if we look to Turkey and the US presidential election. So, but of course, there are methods around for doing that. Okay, that's a statistical problem. How to recognize handwritten characters? Well, this is something you can do with your bare eyes, but you can also try to write a program. How do you do that? Or if you're working in marketing, an online retailer, you want to identify customer target group customers together, such that you can target them with specific ads, for instance, right? Or if you want to predict the function of a protein from its amino acid sequence only, that's a structural biology problem. Okay, so there are many problems. Probably the more you get from top to bottom, the more uncertain you might be about what is a good method. Solving equations, well, okay, that's basic mathematics, right? If you solve them symbolically with paper and pencil, you will solve one equation in one variable and then insert into the other, and you proceed until you finally have the solution. That's a very clear and deductive way of solving problems, okay? Probably in physics, you also have nice equations that you can solve in order to solve the problem. But handwritten character recognition, for instance, okay? How do you do that? You cannot write an algorithm that recognizes what an A looks like, or what distinguishes a B from a C. That makes no sense, okay? you can try to verbally describe what a bee is. It looks like a vertical bar and with two, I don't know, okay, but yeah, but you cannot cast this into an algorithm, okay? I've never seen any real programmatic procedural algorithm that does something like character recognition. But you know that there is character recognition around, right? You're using it when you go to an automatic bank terminal, right? You have a form for transferring money. I don't know how it is in Spain, whether you still have people working behind counters in banks. In Austria, it's the trend that people are removed gradually. Like, there are only machines. Bank only consists of machines anymore. So if you want to transfer money, you have to fill out a form and by a machine. So how does the machine do that? Okay. How does your mobile phone read Chinese characters? Well, I have an app like that on my phone. I can wipe what I want to read, and if it's Chinese characters, it will perfectly read Chinese characters. Most of the time, translations make sense. Not always, but most of the time. Okay. How is this done? This is not done by solving equations. This is not done deductively. This is not done by real algorithms. This is done by systems that are not explicitly programmed to solve a task. These systems are actually programmed, or, well, in the widest sense, programmed by showing them examples. So an optical character recognition software does not have real algorithms with if and for and so on inside. It's a special mechanism to which you present tens of thousands of labeled characters. By labeled, I mean you have all these characters and somebody, maybe a human operator, has labeled the characters saying this is an A, this is a B. So the program knows what the input looks like and what the desired output is. So this is an A, this is a B, this is a C, this is a 9, an X, whatever, okay? And by looking at all these tens of thousands, maybe hundreds of thousands of characters, the system tries to generalize and try to identify automatically, without being explicitly programmed, tries to find out what characterizes an X from a Y, okay? And this is exactly machine learning. It's about learning from data without having a clear algorithm, procedural structure. Of course, it's an algorithm behind it, but the algorithm that's behind it, and I will talk about such algorithms, they are not actually analyzing the data directly. They're just ways of optimizing parameters of this relatively obscure machine learning system, okay? That might sound a little bit vague to you at the moment, but I hope I will be able to convey in more detail how that works, okay? And it's not only handwritten characters, also function of a protein from an amino acid sequence is a typical machine learning problem. And there are so many more, right? Whereas optical things or voice recognition are other examples. Okay, so anybody use, or what is the Google equivalent of Siri? You have a lot of speech input systems nowadays. They're all based on machine learning as well. Okay, so yes.
If you want to do research, no,
Yes.
in machine learning
Yes.
or in deep learning, whatever you say, so what is the potential? Because you say the algorithm is there, no? So what are you trying to do? Obtain better inputs, better labels? What is your contribution?
No, the data is usually given. Okay, so you cannot.
But you need to pre-process the data.
Yes,
clean the data.
yes,
and
yes,
so on?
sure. Well, it's like in every other domain that you have methods that work. Otherwise, nobody would be interested in the subject, and probably nobody of you would be here if it wasn't a subject that's worthwhile.
Yeah.
But there are definitely many open problems, in particular in deep learning. Because deep learning is, to a relatively large extent, a thing driven by handcrafted things, by a lot of experience that you need to have. And there is a lot of theory missing, actually, to explain why things work, in contrast to other things that don't work that well. And if you knew the theory, if you know really what's going on inside, you would also have the potential to develop better algorithms. Deep learning is not the end of the story, I think. There are huge successes. You know that Google and Amazon and Facebook, they're all doing deep learning. Every of these IT giants has hundreds of people, if not thousands, working in deep learning, okay? If there was nothing, if it was a closed subject, they wouldn't do that. And unfortunately, there's a lot of, or fortunately, there's a lot of potential, okay? So, for instance, to make them robust in a way that you just have one button and train something, it's not like that. You have to have a good system, for instance, for voice recognition or for image recognition. You need to play around a long time, and you need a lot of experience. And we're not talking about seconds of computation time. Weeks on systems with thousands of cores. Okay. So I have one example that I will show you tomorrow. It's about character recognition, and it's a very, very basic character recognition example with only digits in a ridiculous resolution of 4 by 6 pixels. Okay. You can solve this character recognition problem really nicely with an accuracy of about 95%. That's pretty good, given the poor resolution of the images. But to find the neural network with the best parameters, that's something that may take days, even for this ridiculous problem. And now if we talk about self-driving cars, that should analyze the traffic situations by looking at multiple high-resolution images at the same time, and where you need reaction times within milliseconds, you can imagine that there is a lot of things that you have to optimize and a lot of things that you have to take into account. So,
yeah, but taking that example, I'm sorry for interrupting.
No problem.
You think that is not correct? Taking that example, when the program, the algorithm learns about autonomous driving cars, no? Really, you need to say, this is a traffic light, this is a new car, this is a pedestrian, this is a motorbike, and you have a video composed by thousands of frames, no?
Exactly.
So you need to annotate?
Yes.
Okay.
Yes.
Okay.
So we at our institute are exactly working in this. What you just described is the process that's called semantic segmentation. So you segment, you partition an image into different objects.
Yeah.
Okay, in a traffic situation, for instance, pedestrian, road signs, road markings, house, vegetation, sky, whatever. And this is
a long task.
This is not very easy, and especially the creation of the labeled data is a horror. It takes a lot of human power. Okay, so, but let's see. Okay, so I think I already made it clear that we might have explicit algorithms or explicit models like we have in mathematics and physics. We have formulas, we have differential equations. And we might have tasks for which we don't have any equations, right? There is no equation for handwritten character recognition. Okay? And in such a case, machine learning from data, is a viable alternative. Okay? So it's about getting knowledge from previously observed data, modeling things, predicting things by looking at previously observed data with the aim to get to obtain insight into what's going on or to predict future outcomes. In the case of character recognition, you're probably not so much interested into getting an insight, what is the difference between a B and a C, but you definitely want to predict future outcomes. What does that mean? Okay, you want to classify new characters, okay? If you have this automatic banking machine that makes money transfers by reading your forms, it will definitely find some characters it has never seen before and will have to make good classifications. That's what I mean by predicting future outcomes, okay? It's about diagnosing future patients on the basis of previously observed patients or classifying handwritten characters on the basis of a model that has been trained on previously observed and labeled data, okay? So it's basically about learning from data. Good. What do we see here? That's one of the most basic setups you could have, okay? You have 3 columns. In machine learning, typically, not always, but typically we have such tables. The columns are features, the rows are samples, okay? In this case, we have 2 numerical columns and 1 column that obviously only consists of +1 and -1. This could be, for instance, a medical diagnosis situation where the first 2 columns are 2 clinical measurements, I don't know, blood pressure and heart rate, for instance, and the doctor has to make a classification where +1, positive, always means negative for the patient. You have some disease, and negative means you don't have it, okay? And if we look at that, well, putting it simply, the goal of machine learning is, in this case, to predict for a new sample for which you have these 2 measurements, whether it will be +1 or -1, healthy or diseased, okay? And we want to identify the algorithm, the method, the model that makes this prediction by looking at all of these samples, all of which are labeled with the correct, hopefully correct label, okay? This, what you see here, is not so spectacular. By looking at such numbers, you probably don't see anything. But if you visualize them in this way, you may get an impression about how the 2 columns, the 2 numerical columns, relate to each other, and you probably see it even better if you also label all of those spots. Every spot is a sample, and you label it with the class, okay? So what you see here is every spot is 1 such sample, right? On the x-axis, you make the spot at the first value. On the y-axis, you make the spot where it's the second value, and the color means blue is -1, red is +1, okay? And then you immediately see, well, we can actually classify them. If we put a linear separation between the blue and the red dots, if there is a new dot here, what is the supposed class? Red. And if it's up here, blue, okay? And maybe in between there could be some twilight zone. We don't know yet. It doesn't look like there is a twilight zone on this example, but there may be other examples like this one, okay? So it's not a simple line that you can draw. So maybe there is a large twilight zone that the 2 things are overlapping because of noise, or maybe there is a complicated nonlinear separation between the 2. Who knows? Okay, these are all questions that you have to ask yourself. Okay, this is another example. And this is another example where obviously the separation is good, but it's not at all linear, right? We have lower left, upper right in blue, upper left and lower right in red, okay? So if you start from a linear model, you will never be able to solve this one. Okay? You have to do something else. In reality, it's never like this. You never have only 2 inputs. Okay? If you think about handwritten character recognition, the number of inputs you have is the number of pixels, which is, in the end, a pretty high-dimensional space. Okay? It could be in the hundreds, range of hundreds of pixels. Okay? So here's an example where you have far more than two such columns. We have 6, and this is still a handcrafted example. You might have up to tens of thousands of such features. If you're thinking of a high-resolution image or a speech signal with kilohertz sampling, okay, then you can imagine that this is a truly high-dimensional space. And so machine learning is not only about drawing such so-called scatter plots and coloring dots and playing around with lines that separate the two classes. Yeah, that's a good start maybe. But in the end, we're talking about things that are like this or much more complicated than that. Okay? So just to give you some idea, I'm sorry, I have to come up with this ancient example again. It's actually from a 2001 book, but I think the first edition of this book was from 1973. So when I was about that size. It's a good example, and I think it fits nice to a city like Malaga, where you have port and you have fish. I don't know whether you have fishing industry here. Maybe the sea is already empty.
Well, expect the process, the fishing.
Yeah. Okay. No, it's a hypothetical example about fish sorting. Okay, it's a very simplified example because there are only two kinds of fish, salmon and bass. Okay, I don't think any of those two are very common here, but okay, you can also think about, I don't know what they are, melusa and bacalao or whatever. Okay, so this is about sorting bass and salmons automatically. Okay, so suppose you have a conveyor belt, and previously humans were sorting them because they need to be sold differently, they have a different price. And now a neoliberal young manager comes and wants to replace the humans by an automatic system. And so there's a camera that takes an image of the fish every time it comes by. And then within, I don't know, 1 second or so, the computer has to make a decision whether it goes on the left or the right pile, into the salmon basket or the sea bass basket. Okay, that's what they look like. For a human, it's very, very obvious that they look very different. So they have different shapes, different fins, different color, different scales. Okay, but if anybody of you has ever done computer vision or image processing, probably know that to compute features about scales and fins is a very complicated thing. Okay, so maybe we want to start with a very, very simple approach. Just look at the size of the fish, because maybe it's known that salmons are a little bit shorter than sea bass, and that maybe we look at the color here in the middle. Maybe it's known that sea bass and salmons, they don't have the same color. And now we record with image processing how long and how bright the fish appears. And then we want to create a data set and classify the fish automatically with a database, with a very, very crude, simple machine learning system. Okay? Okay. Taking only length, if we have, in this case, 120 examples, you have this data set in the course material. Okay, so you can download it and look at it. It consists exactly of something like that. Looks exactly like this. Maybe this is even the fish data set, I don't recall. Okay, so you have length and brightness normalized to a range from 0 to 1, and you have +1 and -1 as far as I know, as far as I remember. +1 is sea bass and -1 is salmon. Okay, good. So the first question is, can we separate the two fish classes just by looking at length or brightness alone. And if we look at the length and draw a histogram of these 120 fish samples that have been labeled manually, you see, well, generally, salmons are shorter than sea bass. But there is a huge overlap, a twilight zone. Okay? So if you draw the threshold somewhere here, all of those purple bars, all of those samples stemming from all of those samples that create the purple bars in this histogram here, above the threshold will be misclassified as sea bass, and all the sea bass below will be misclassified as salmon. So we will get a lot of misclassifications, and the company will not be really happy. Okay? Why is a company not happy about that? Well, if you misclassify things, it's always bad, right? If your form is misread, maybe the money goes to the wrong bank account. Okay? And here, it's the same thing. Okay? I've been told by others, actually, I always thought salmon would be more expensive. No, it's actually sea bass that is more expensive. But if you sell a salmon for a sea bass, then maybe customers will complain because they get the cheaper fish. And if you sell sea bass as salmon, maybe the customer will be really happy, but the company loses money. Okay, so you don't want to misclassify any of the fish. And if you look at brightness alone, then you see it's much better, right? Again, salmons are darker than sea bass, and if we draw a threshold here, we may have something like 6 or 7 or 8 misclassifications out of this 120. Still not perfect, but at least better than to look at length alone. Okay, yeah, but who tells us to use only one feature, only length or length or brightness? Why don't we take both together? And that means we end up at such a scatter plot. And then you see, well, since obviously both are related to the kind of fish, they carry information also when they're taken together. Okay? And now you see much better, okay, there might be something like a linear classification here, but with a twilight zone. So maybe systematically it's impossible to have a perfect algorithm because there are some unusually short and dark sea bass and some unusually long and bright salmons, okay? Though generally the separation is quite good. Okay, so why not do this? That's a very important slide, by the way. Why? Well, on the one hand, it seems that this solves the problem perfectly, right? We have 0 misclassifications. Okay? Every red dot is on the pink side, and every blue dot is on the light blue side. Fantastic, right? Or no? What do you think?
Yeah.
You don't like it? Okay, me neither. Because I think it's actually a twilight zone, okay? What we do here is we just handcraft the classification border such that it actually fits to this data. But what happens actually if the next day you measure a new fish, okay? And the 2 values are here. What do you think? Will it be rather salmon or sea bass? Blue or red? What is more likely? Blue, yeah. And here, it will be more likely red, yeah. What is the deal? You have to distinguish signal from noise, right? The answers that we gave look reasonable to all of us, but it's not 100% clear that they're true. It's always a matter of signal and noise. So there is maybe a perfect separation, but the data are noisy, okay? Because of measurement errors, or also because brightness and length of a fish has some random variations into each direction, okay? So if it's actually a relatively simple rule that separates the two kinds of fish plus noise, then this is the better solution. If there is no noise and there is a very, very complicated systematic behind the separation between salmons and sea bass, maybe this is the better solution. What is in any case true is that it's completely pointless how well it works on our pre-recorded samples. What is most important is that it works the next day, because you don't want to classify already classified samples. You want to classify the new fish that are coming along the belt, right? Because that's the thousands of fish the company is selling. And the more misclassifications you have, the more money the company loses. So it's not about getting perfect results on the already known samples. It's about getting good results on future data. Oh, that means we have to know the future. That's not generally a difficult thing, right?
Yeah.
So is this where machine learning ends already? Because we need to know the future? No. I want you to take the following messages, okay? It's all about the performance on future data, okay? You don't want to diagnose patients that have already been diagnosed. You want to diagnose new patients. You want to classify new characters. You want to classify new fish, okay? And the performance on the new data in a real production environment or real clinical environment is important. It's not the retrospective thing that is important, it's the prospective thing that is important. That's the first take-home message. The second take-home message is that by looking at the data in this way, you do not know where is the signal and where is the noise. That means you need to have a certain model of the future to estimate what is the best solution. Okay, so all of these questions more or less summarize what I just said, okay? And putting it into a different perspective, now machine learning is about describing previously observed data, but in a way that it's useful for future data. Okay, good. There is a distinction between two types of machine learning. It's unsupervised and supervised machine learning. All that I have talked about so far is supervised machine learning. We want to classify things. We want to predict things. We want to find a relationship between an input and an output. For instance, images and what class it is, or length and brightness and what type of fish it is, right? There is also, so supervised in the sense that a teacher, a hypothetical teacher, tells you what the right solution is, okay? Unsupervised machine learning is something that I haven't talked about yet, and I will not talk about today. It's about finding structure in data that might be useful without having anything to predict, without having any labeling, right? It's just data, and you want to make sense of. Clustering is a typical unsupervised methodology, or principal component analysis, if you have heard about it. But this is something I will not talk about now, okay? In the case of supervised machine learning, we distinguish between classification and regression. Classification is what I have talked about now, like digit classification, fish classification, medical diagnosis, that's all classification. So you have classes, good, bad, healthy, diseased, 0, 1, 2, 3, 4, 5, and so on. Salmon, sea bass, whatever, okay? There is a second type of supervised machine learning. It's called regression, when you predict a number, right, on a continuous scale. Like you look at the weather the last 3 days, and you want to predict the weather in 3 days, the temperature, for instance, right? The temperature is not a +1, -1 thing, okay? Maybe in Austria in winter, but but not here in Malaga. Okay, it goes on a continuous scale, right? And that's called regression. So yes.
You said that classification is for labels, but you give me examples of like positive or negative, something like that. What if it's like a movie genre, like that there are many and they're not like opposite, they're just different.
Yes,
How
yes,
do you
yes.
classify that?
My examples were 2 classes, but there is no general restriction that there can only be 2 classes. Okay, so classification can have any number of classes. But digit recognition, for instance, or character recognition has several classes. Okay, categorization of movies, that's a particularly difficult thing because you have so many categories. You have a huge number of classes. That means even if you have a large data set, the number of samples belonging to each of the classes is relatively small. So that's generally difficult, but it's not impossible. But there is no restriction that classification only works for 2 classes. It's largely true for support vector machines, but I will talk about that later. And there are even ways of extending support vector machines to multiple classes. Okay, well, thanks for the question. Okay, I will skip this. Maybe this is important to make clear about what I'm talking about, especially the difference between model class and model. Okay, the model class is a coarse framework in which we're looking for solutions. Okay, and a concrete model is one instance, and we try to find the parameters. Maybe this is best explained with linear regression. Do you know what linear regression is? Okay, so you have some dots, and you want to fit a line. Okay, and this function here expresses y as a function of x, where it's k times x plus d. K is the slope, okay? And d is a vertical offset. The statisticians call this intercept, okay? And the model class is the set of all possible lines, okay? A concrete model is one where you have a concrete k and a concrete d, okay? And those are the parameters, okay? And typically, we start from a model class. Every machine learning algorithm defines a certain model class and then searches for optimal parameters that fit best to the data. In very crude terms, that's basically what happens. Okay? So that explains the difference between model class and model. Okay? A model is a concrete instance that you can use to predict. A model class is just the larger class of the algorithm. Okay? And the way of fitting the parameters of finding a concrete good model is called training or model selection. There might be some extra parameter that you cannot directly optimize, but you might have to find a good choice as well. So for instance, if you don't do linear regression, but polynomial regression, then the degree of the polynomial is a discrete parameter that you cannot directly optimize, okay? Or maybe you have a learning rate or some weird parameter that parameterizes the algorithm by itself or something like that. This is called a hyperparameter, but you also have to find good hyperparameters. Okay. Good. What happens? So typically we start from a question and data, and you do pre-processing. You may have to choose features. You have to choose a good model class. You have to train the model. You have to evaluate the model. And at every step, things can go wrong, and you might have to reiterate things. Okay? So this is it's not a workflow in the sense that it just goes down like a pipeline. All of these reiterations and all of these steps in between require an intelligent human being, a data scientist, if you will. who is able to judge the results, whether they're good or not, to finally come up with a model or an answer, or to finally come up with the decision, no, it doesn't work. Okay? Because it's not so that machine learning solves everything. If it was so, machine learning would already have solved everything. But this is not true, because there are things that you cannot predict. You might think that your data contain information, but you can never be sure until you try. Okay? And that you may come to the point that you seriously say, no, sorry, I can't do it. Okay? But there may be some very obvious situations. You cannot diagnose a patient on the basis of the name of his mother-in-law, right? That makes no sense. That's probably statistically independent. Who knows? But okay. But there are many situations in which it's not really obvious. Okay. So if you have a machine and you think that the measurements in the machine allow for predicting the product's quality, and maybe you simply haven't done the right measurements, or maybe there are random fluctuations in the production quality that cannot be modeled. Okay, you never know. So that's why in many cases you can be happy with having obtained a solution, and in some cases you have to be honest enough to say, no, sorry, it didn't work, which can be really bitter in case that a lot of money has been invested into the research and into creating the data set and so on. Okay. Good. So the basic ingredients, I think that should be clear. We have to start from a model class. We have to have an algorithm that optimizes an objective, but we have to make clear what the objective is. So for the fish example, we may want to minimize misclassifications of future data. Okay? That's one way of doing it. That's not necessarily the only way. Sometimes you may not be interested in misclassifications. You may be interested in sensitivity, specificity, and things like that. I will talk about all these things. Okay. Good. So to close this, as I told you, machine learning can do tremendous things. They have become standard tools in a variety of disciplines, and I will show you several examples. But on the other hand, you cannot solve everything in the world with it. If you have good differential equations, why replace them by an approximation? Makes no sense, okay? And there may also be some things that can simply not be solved, okay? As I told you, diagnosing a patient on the basis of the first name of his mother-in-law, that makes no sense, okay? Good. And what is also important is that machine learning should not be applied in a naive way. Typically, throwing data into an algorithm gives you a result, but it takes a lot more to get a really good result, and it's really important to know whether it is a good result. You need to be able to evaluate the things properly. And there are so many pitfalls that you could misguide you, that you think you have wonderful results, which are actually not so wonderful. Okay. Good. So let's move on. No. No, there is. Okay. There we go. Okay. So I already told you what the goal of supervised machine learning is. It's to identify the relationship between inputs and some labels. Okay? Like here. So here I have another example where we want to classify tumor types on the basis of gene expression values. These are only 6 features. Typically in gene expression we have tens of thousands of genes that are measured simultaneously by microarray, for instance. Okay. In this case, you see that gene number 5 has generally lower values in tumor type B than in tumor type A. But to find that may take some special methods and time, especially if you have tens of thousands of genes. Okay? And maybe there are multiple genes interacting in a way that is not so easy to find anymore. Okay. So I told you about predicting things for the future, right? And that it's not important that we properly deal with data that have already been measured and classified. We want to have systems that work nicely in the future. But it's impossible to know the future. In machine learning, we typically assume that our model of the future is a probability distribution. It's a probability distribution that tells us how likely it is to observe a certain input and a certain output. So for instance, it's highly likely that a long and very bright fish is sea bass. It's not so likely that a long and very bright fish is a salmon, right? And vice versa. Okay? So that's captured. We don't need a crystal sphere that tells us this fish comes the next day. We just need to know how lengths and brightnesses are distributed for salmons and sea bass. So that's fortunately much simpler than really predicting which fish is coming next. Just we need to know the distribution. But the bad news is, for complicated practical problems, we don't know this distribution either. Okay? What is the distribution of handwritten characters? What is the distribution of bees in the list of handwritten characters over the image space? Okay, it makes sense to ask that question, but you will probably never be able to give a good answer for that. Okay? The good thing is we will not necessarily need this distribution to be able to do proper machine learning. But actually what we want to do with this distribution is to find out what the expected error on future data is. What is my error if I let this model run in the fish packing company from the next day on? Okay? What is my classification rate? Will I have an error rate of 3% or 5% or something like that? Okay, that's the only thing I want to know. So this distribution is would only be used to calculate the misclassification probability. Since we don't have this distribution, we cannot calculate this misclassification probability, which is bad. But there are some tricks for doing that. If we don't know the future, let's simulate the future. Concretely, that could mean the following. If you have 1,000 fish images, right? And you train your classifier on these 1,000 images, then you don't know what will happen next. But you can take, let's say, 200 of those fish images, randomly pick them, put them away, and train your system on the remaining 800. So the training of your model has never seen the other 200. The other 200 are as if they had come from the future. If the distribution of lengths and brightnesses of fish does not change, if it's always the same, and if we picked training and test samples randomly, then this is actually an unbiased estimate that we can obtain for the classification error on the basis of these holdout samples. Okay, is that argument clear? So that's, I think, a very, very simple way of simulating the future. Okay. The only problem is if you have a limited number of samples, you cannot use any sample both for training and testing. Okay, that's not possible, and that's statistically invalid because your model is biased to your training samples, and you can only test the model with samples to which the model is not biased. So the problem is what split to do. If you take very few, so generally the models are better the more samples you have taken. And the estimation of the generalization error is better the more test samples you take, okay? And if you can only split them, if you have very, very few training samples, you have a very poor model, but you can perfectly estimate how bad it is. If you have very many training and few test samples, you have maybe a very good model, but you cannot estimate how good it is. Okay? And in order to avoid this problem, there is the trick of cross-validation, where you split the entire data set into random folds, and you always train with all samples except one fold, and you use one fold for testing. And you always have an unbiased test set, and you do this for all folds, like in this picture here, and then you can average the results. So in this case, every sample is only a test sample once. The training sets are overlapping, but that's not a problem anymore, okay? Good. I will not go into detail about that. That would take too much time. This is about how to evaluate classifiers, what is a false positive, what is a false negative, and so on. I will skip that. Maybe you can go through the slides yourself. I just wanted to tell you that accuracy is a very, very common way of measuring the performance of a classifier. Accuracy is just the ratio of correctly classified samples, okay? That's what it comes down to. And I just wanted to tell you that accuracy is not a very good measure for unbalanced situations, for instance, where you have 1% diseased patients and 99% healthy patients, okay? If you diagnose everybody not to have the disease, you're 99% right, okay? The accuracy would be 99%, although your diagnosis doesn't do anything, okay? That's not good. That's why we typically have some things like sensitivity and specificity, and the balanced accuracy is the average of sensitivity and specificity. But I will not go into detail, but this is just a little glimpse on what might be important if you have unbalanced data, okay? This is an important thing. Underfitting and overfitting, okay? What is this? Underfitting means, I told you, it's always about signal versus noise, right? Underfitting means that the signal is more complicated than what I suppose it to be, okay? So for instance, if the separation is like this, and I just use a straight line, then I cannot capture the complexity of the data. I do not capture the signal. And overfitting means my model is too complicated such that it starts fitting to noise, right? If you understand this as if you have a hyperparameter that adjusts complexity, right? I will show you a relatively simple example later on. Then what happens typically is that if the complexity is too low, then both the training and the test error, so the error on the data you fit to, that's the training error. And the error on the new data, on future data, they're both high because you don't have the capacity to really model the signal, right? So if it's like this and you just draw a straight line, then it's not good, okay? But if it's, so let's do this, okay, I have one class here, one class here. If I just use a straight line, then I cannot capture some of the parts nicely, okay? And if I start doing this, maybe I do this just because of noise, okay? That is called overfitting. This is really important, and in most machine learning algorithms, you can adjust complexity, and you have to face this problem that you have to find hyperparameters such that you get the sweet spot here in the test error. That the training error is low is pointless. Okay? The important thing is to get the test error to the lowest point. Okay? So that you balance underfitting and overfitting properly. Just as a simple example, the k-nearest neighbor. Has anybody ever heard about it? K-nearest neighbor classifier. What it does is very simple. Let's start with the one nearest neighbor. You have your data set. And if you have a new sample, like here, you just look what is the closest training sample and look what class it has. And since this is blue, I classify this sample as blue. And here the closest sample is this one, so I classify it as red. Okay? That's the one nearest neighbor. The problem is the one nearest neighbor is if you have noise or outliers, they always create an island around this sample. So it's very scattered and it might overfit. Okay? The k-nearest neighbor, the general k-nearest neighbor has the following approach. It not only looks at the closest neighbor, but at the closest k neighbors and takes the class that occurs most often. Okay? So if I'm here, for instance, and I have the 5 nearest neighbor, then I have 1 blue and 4 red samples around, so I will classify it as red and not blue. Okay? So here, for instance, k equals 5, 13. And you see the larger k gets, the more it smoothens the whole thing out. So with the k, the number of neighbors you can consider, you can balance underfitting versus overfitting. Okay? Maybe this is already underfitting. This is surely overfitting. Okay? Linear regression. I told you already about linear regression. You want to fit a line to minimize the vertical distances between the points and the lines. You can do this for one-dimensional data with one input and one output. You can do this for multi-dimensional data. And you can also generalize it to polynomials, here with a degree of n, right? And then suddenly n is a hyperparameter with which you can adjust complexity, right? So if you have something like this, it obviously looks like a cubic polynomial plus noise, right? This is underfitting or overfitting? Underfitting, right? For n equals 2, it's the same. N equals 3, 4, 5 looks pretty good already, okay? If we have a degree that is too high, we start fitting to noise, obviously, right? So that's overfitting. It's actually a polynomial of degree 3 plus noise, and the more we increase the degree, the more we start fitting to the noise. Actually, to things that aren't there, that are just random. So I hope that these two examples, one for classification and one for regression, makes clear what underfitting and overfitting means, and makes clear that you might have to address this trade-off between underfitting and overfitting whenever you do machine learning. Okay. How much do I have time? From now on? No.
12:30.
12:12. Okay, good. So I think in the interest of time and in the interest of deep learning, I will go really quickly over support vector machines.
Yeah.
Support vector machines are, from the general idea, really very simple. They are linear classifiers, but not arbitrary linear classifiers. They're linear classifiers with a twist, so they try to use not an arbitrary separating line, but a special separating line that maximizes the distance to the samples. Okay, so you try to put the widest tube between the two classes. And the reason is very clear for that, because if you start jiggling your data, that's only an intuitive explanation. If you imagine you're jiggling data, right? If the separating line is as far away from the samples as possible, then the jiggling doesn't have such a high risk of creating a misclassification. If you put your classification border here, then jiggling this sample can easily create a misclassification. So that's, in intuitive terms, the idea behind support vector machines. That's only a very crude explanation. In detail, it means a lot more, right? So you have to solve a quadratic optimization problem and so on. But the good thing is, you can generalize it in a way that the data need not be linearly separable anymore. And you can even generalize it to a nonlinear variant that actually works via a so-called kernel, which is a positive definite similarity measure. And then you can interpret it as a linear classifier in the high-dimensional Hilbert space. If that only means, I don't know, Chinese or any foreign language to you, forget about that. It's the only thing that you need to know is that you need to have data and you need to have a similarity measure on the data. And then you can train an algorithm in a very, very nice way, namely that you have a very good theoretical property that you minimize an upper bound on the generalization error. So it really works nicely. You have very few hyperparameters only. And since you only need a similarity on your data and not necessarily a vectorial representation, this opens up the field to various applications. So for instance, think about images, think about signals, think about biological sequences. You can have similarity measures quite easily. Chemical compounds, for instance, right? So you have structural formulas of compounds. You cannot easily cast chemical structures to a vectorial representation, but you can define similarities relatively easily. Okay? And as soon as you have such a similarity, you can use support vector machine. So that's a very, very nice and general method that generally gives really, really good results. You have a guaranteed optimum because it's a quadratic optimization problem with linear constraints. It's a very, very good method, especially if you have few data. I will later talk about deep learning. Deep learning is a perfect method if you have large data sets, but it works really poorly for small data sets because you have to fit a lot of parameters, and you cannot fit a lot of parameters to a small data set. And here we only have relatively few parameters and very few hyperparameters, and this is something that works really nicely for small data sets. Okay, I will not go too much into detail. I will just show you a few examples of a linear and a nonlinear support vector machine, and if you do it wrongly, you can even overfit. Okay, so there are still hyperparameters with which you can overfit even with a support vector machine if you do it wrongly. There is no machine learning method that is perfectly safe. Okay, if you do things wrong, they will go wrong. Good. They are generally defined for two-class problems because you cannot put a tube between more than two classes. Makes no sense. Okay. But there are some approaches that circumvent this problem. And the most common approach is the pairwise classifier approach, where you train the support vector machine, multiple support vector machines on pairs of classes, and then combine the result. This is all I want to say here because time is limited. Okay. I also can show you an example that if you have a proper similarity measure for biological sequences. Are there any bioinformaticians in here? Yeah, okay, good. I will show you this example tomorrow. Okay? You can have a sensible similarity measure of biological sequences, even if they are not equally long. Like amino acid sequences, they're seldom of the same length. They're not aligned to each other. But even in such a situation, you can have similarities and you can do sequence classification really, really nicely. I will not go into the details. I will show an example tomorrow. Okay. Let me move on to something completely different, another machine learning method that is very common and that gives almost always very, very good results. And those are random forests. that sounds really strange. Okay, what is a random forest? Okay. Well, support vector machine is also a questionable term, I think. But I will not go into details why they are called support vector machines. But I can show you a little bit what the reason is why random forests are random forests. Okay. Before I talk about a random forest, I have to tell you what a tree is. So you probably think you know what a tree is, but this is something else. Okay. So I'm not talking about real trees. I'm talking about decision trees. A decision tree is more or less a classifier that consists of nested ifs, if else. Okay, that's basically it. So you successively ask a question. If this is true, then do this. Otherwise, do this. Okay, and every sample that you want to classify goes through this hierarchy to give a final answer. And what are the questions? The questions relate to input features. So I'll give you an example here. Maybe you have heard about the Iris dataset. It's a very old data set, a true classic in statistics. It's a data set consisting of 150 iris flowers. And for all of these 150 iris flowers, there are 4 features: sepal length, sepal width, petal length, petal width. Okay, so these are 4 measurements about the flower itself. Okay, and there are 3 types of flowers, and there are 50 samples of each. They're called setosa, versicolor, and virginica. Okay, and this is, for instance, a very simple decision tree that could classify the 3 classes. So if you have a new sample, you first ask the question: is the petal length smaller than 2.45? If so, it is setosa. Otherwise, you ask another question: is petal width smaller than 1.75? If so, it's versicolor. Otherwise, it's virginica. Okay. So here you see in this diagram, you see a scatter plot of those 2 variables, petal length and petal width, that the tree uses. It's actually 4-dimensional, but I only used these 2 dimensions because these are the only 2 that are actually occurring in the tree. Sorry. Okay. And you see here, obviously, setosa, that's the red class, can be nicely separated by this threshold here. So everything to the left of this vertical border is obviously setosa. Okay. And then, if we classify the remaining data, we still have the other 2 classes, versicolor and virginica, and it seems to be good to draw a threshold here. So you see all the blue samples up here are perfectly classified. All the green samples are below, and we also have 5 virginica flowers that are misclassified as versicolor. Okay, that's one way of doing it. That's a decision tree. The question is, where does this decision tree come from? Who comes up with this? Well, this could be expert knowledge, but then it wouldn't be machine learning. Machine learning, we try to find a good tree, so we are asking the questions and we try to find the questions, such that in the end, in the leaves of the tree, if we propagate the entire training set through the tree, and every sample falls into one of the leaves, okay, ends up in one of the leaves, then the leaves should be as homogeneous in the class as possible, because then I have a good separation. If asking the question doesn't do anything, and I still have 1/3 of this, 1/3 of this, and 1/3 of this in every leaf node, that makes no sense. So you see here, what I have done is I asked the questions in a way that only setosa samples are here, only virginica samples are here, and hopefully, or almost only versicolor samples are here. Okay? So I want to have maximum homogeneity in the leaf nodes. If I propagate the entire data set here, we have the 3 classes equally distributed. And here, this is homogeneous, this is homogeneous, this is almost homogeneous. Okay? So there are different ways of doing this. Okay, I will not go into the details. So it's an information theoretic thing. You just try to choose, in every step, you choose the question that gives you the best gain of homogeneity. Okay, that gives you a gain in information, so to speak. Okay. There are multiple approaches. All of them come from all of them have to do with the distribution of samples or maybe entropy and things like that. Okay, but I will not go into details because of the lack of time. Okay. So I told you what a single tree is. What is a random forest then? A random forest is an ensemble of trees, of random trees. So if you have random trees, you get a random forest, no? Why are we doing that? So generally, it has turned out in machine learning that it's always good to view things from a different angle. If you have multiple models, an average over multiple models, you typically get more robust and less overfitting models than if you take a look at one single model alone. So, what is random about a random forest? The shocking news is that if you train a decision tree with a data set, it's a deterministic algorithm. It always gives you the same tree. There is no randomness involved. So you cannot have a random tree. If you have a random forest with 10,000 trees, and you just train every tree on the same data set, you will get 10,000 identical trees. So the ensemble will be of no additional use. So there needs to be some randomness. The randomness comes from two sides. The first side is, if you train multiple trees, then you never train the tree with the entire data set, but only with the subsample of the data set. What does that mean? So suppose you have, let's say, a few outliers in your data set, then most of the trees that you train will not have this outlier. Keep that in mind, because in the end, when we classify a sample with a random forest, we classify it with all the 10,000 trees, and then look at which class has occurred most often. Okay? So if most of the samples do not, most of the trees do not contain the outlier, it means that the trees that have been trained without the outliers will overrule the few unlucky ones that had the outliers in the training sets. Okay? So that will make the whole thing robust. That's the one thing. The second thing is, at every split, so when we create a decision tree, at every split, we can have a multitude of different splitting criteria, of different splits, like petal length at this threshold, petal length at any other threshold, petal width, sepal length, sepal width at any other of this, at any threshold. Okay? The trick is, or the problem of decision trees is, if there is one variable that clearly dominates all the others, it will always appear first. It will always be greedy. Okay? Like petal length here. And the trick in a random forest is, when you train a tree, for every split, you only take a random subsample of features. That means that from time to time, the best feature is overruled by something else. And that means that the trees all have different approaches to the same problem. They think they have alternative views in there, which makes the whole thing much more robust. Okay, look here. This is a random forest classification of the iris dataset. So you see Setosa is always properly. So this is an average color of what the random forest, or the trees in the random forest, this 1,000 trees say. Okay, so you see they're always right about Setosa, but obviously you see that approximately half of the trees make this split first, and half of the trees make this split first because of this random feature sampling. Okay, and you also see that finally, since we have so many trees that this little edge here is much better captured. And maybe we have only 2 misclassifications where we have 5 here. Okay? And you can really model very, very complicated things. Random forests also have a huge advantage that you can even estimate, and that's a fantastic thing. You can even estimate generalization performance by looking at the training set only. How can you do that? Since every tree only uses a subsample of data, you can always use some unused samples for estimating the tree's performance. In other words, you start from one sample and you estimate its prediction on the basis of those trees that have not used this sample. And you do this for every sample, and then you can average. And it has been shown by Bryman that this is an unbiased estimate of the generalization error. And you do not even have to train something else. You don't have to do cross-validation. You don't have to withhold anything, because the withholding takes place in procedure of the random forest. And that's an absolutely fantastic thing. That saves a lot of time. Okay? And you can also measure variable importance by looking at which features occur in which way. You can measure variable importance, which helps greatly with understanding what's going on in the random forest, which is largely a black box, because thousands of trees you cannot comprehend. That's a little bit absurd, because a single decision tree is very nicely interpretable. You can read it. You can show this iris decision tree to everybody on the street. He or she will immediately understand it, okay? But 1,000 or 10,000 trees, no chance. Okay? But these ways of measuring variable importances can be used to get a little bit of a glimpse of what is important. Okay, I will not go into the details here. I'll show the results for the iris data set. So you see here that for 2 different variants, how to compute the variable importance. In both cases, petal width and petal length are almost equally important, whereas sample length and sample width are less important. And this is really, really useful. I can, unfortunately, I don't have it on the slides, but I can show you, I can tell you about a little example that I did myself. Well, it's not so little, actually. It's a project I did with the university clinic in Linz. It's about identifying risk factors for heavy heart surgeries. Okay, so maybe you have heard about a heart valve surgery. Does anybody know what a heart valve surgery is? So if the heart doesn't work anymore because the valves are damaged. Okay, so the heart is a pump actually, and the pump needs valves. Okay, otherwise, so the blood needs to be released when the heart is pumping, and needs to be blocked when it's pumping to the other side. Okay, if it goes back, then it doesn't pump properly. So if the heart valves are not properly working anymore, then it means that your heart is not doing well. Okay, and it has problems to transport oxygen through the body. So problems with the heart valve are finally lethal. Okay, it gets worse and worse, and after a few years and so on, people die. Okay, because of heart failure. So it has become a standard procedure to replace heart valves by artificial valves, and I think there were also pig transplants, which are no longer used. Yeah, it's true. It's true. Yeah, you can live with pig valves in your heart, but now I think they have artificial heart valves. What happens is they cut you here, they open your chest, okay? Then they stop the heart. The heart function is taken over by a machine, heart-lung machine, okay? And while if the heart is deactivated, it's like a bag, like an empty bag. They can cut it open, replace the valves, and then they close everything again and they try to restart the heart. That's basically it. That the whole procedure takes about 8 hours. Your heart is stopped and restarted. Your chest is opened and closed again. So this is a really heavy thing, okay? it's unimaginable for a non-surgeon like me that it works at all. The overall death rate after 30 days after the surgery is 3%. Okay, that's amazingly little, given how severe this intervention is, but it's of course far, far higher than like a routine surgery. Okay, like removing the appendix or so, where it's a risk of 1 out of a million or something that you die from this. But if 3 out of 100 die after such a surgery, that's a relatively high death rate. Okay. What do doctors do when they try to persuade somebody to do the surgery? They say, okay, 97% chance that you make it. Okay, don't care about the 3%. Okay? If it was only a random thing, that would be the only thing they could do. But suppose there would be any indicators that let you predict who has a higher risk to die, that would really help in decision making for the patient and the doctor as well. You get the point? Okay. So, but nobody ever looked at that. That's not entirely true. Okay, there are some risk indicators, but they don't work that well. What we did is we looked at all heart valve surgery at Linz General Hospital, now Kepler University Clinic, from 2008 to 2014, I think. There were 2,229 cases, okay, of which 3% died within the first 30 days after surgery. And for all of them, we had a lot of measurements. Well, starting from age, weight, height, sex, previous diseases, and all the measurements that are taken. If you go to hospital, they make a lot of tests before surgery, right? And then we had several hundred columns. And what we did then is we tried to predict the 30 days mortality after the surgery from these hundreds of variables. The problem was that it's very unsymmetric. It's 3% dead and 97% alive. So accuracy is not a good measure, because every machine learning method says, whoa, 97%, perfect. Okay, if you predict everybody as alive. Okay, so we had to do some special tricks to optimize for area under the RC curve, for balanced accuracy and things like that. But actually, it really worked out well. We now have a scoring mechanism on the basis of this random forest that we used that performs better than the Euroscore, which is the standard risk assessment score used in heart surgery in whole Europe. Okay, and we can really, so the ones that we predict as the 10% with highest risk actually really have a risk of 25% to die, and not only 3%. So the separation, it's far from being perfect. Okay, it's not that we with 100% accuracy say you will be dead, you will be alive. Okay, but at least you can tell the patient you have a 25% risk to die, and to the other you have a 3% risk to die. Well, maybe it doesn't really help the 3% guy because it's the same information that he would have gotten before, but the 25% guy will have to reconsider. And with this variable importance thing, we also could identify risk factors. And interestingly, kidney parameters turned out to be the most important and the most predictive features. We don't have any medical clue why this could be the case. We don't think that it's causal. Okay, we don't think that kidney influences mortality after heart valve surgery. But what we think is that kidney parameters are a general proxy for the general condition of the patient. And if the general condition of the patient is bad, the patient has a higher risk to die. Okay? But this is all what we did with random forests, and it was really successful. And I also did support vector machines and deep neural networks and random forests, along with these very simple tools, work best in this scenario. Okay, good. So, any questions regarding random forests? What is really fantastic about random forests is there are almost no parameters that you have to deal with. Then you just choose a large enough number of trees. The good thing is the larger number of trees, or a larger number of trees doesn't lead to more overfitting. Okay, just leads to better estimate and longer computation times. This is more or less the most idiot-proof machine learning method I have seen before. You just drop in your data, and if the data is not unbalanced, there's more or less nothing you have to do. You just choose a large number of trees, and it will work out nicely. Okay, it doesn't mean that it is generally the best method, but it always gives you a good baseline. Okay, now let's make a 180 degrees turn. So from a method that is almost idiot-proof, that works for everything, but not necessarily in the best way, that was random forest, let's move to a diva, okay? To a method that can do fantastic results, that can achieve fantastic results, but which might be a little bit difficult to deal with, okay? Like a diva, okay? Forgive me this metaphor. Okay, what is the general idea behind a neural network? Okay, so already in the 1940s, so about more than 70 years ago, when computers came up, people thought, well, the obviously most intelligent thing that evolution has come up with is the human brain. Okay, and if we are able to model a human brain in a computer, we can create an artificial intelligence. Okay, it may sound a little bit naive, but it's not totally nonsense what they thought. Okay, of course, in the 1940s, they did not have the computing capacities to remotely be able to simulate a human brain, which consists of billions of computing units. But at least the idea has been created at that time. So an artificial neural network, in those cases people just say neural network, okay, is a massive parallel processing system with small computing units that work in a way that is similar to brain cells. So it's basically about having a massively parallel system of little units, each of which is relatively dumb, but which all together, with their vast complexity and all the interconnections, are able to perform magnificent things like the human brain does. Okay, good. Let's talk about how such a neuron works. And it's astonishingly simple. Okay, this image really looks complicated, but I will not talk about the molecular biology and the microbiology of that stuff inside. It's basically an electrical thing that is important. Okay, every such nerve cell carries an electric potential, right? The potential is changed by inputs. These are these little branches called dendrites that take up charge from neighboring cells. And these potentials, they may be positive or negative, okay, can increase or decrease the potential in the cell. And what happens is, if the cell's potential exceeds a certain threshold, then the cell fires away, gets rid of this potential, which is fired through this output unit, this axon, okay? So it's like a little program that says, okay, I'm gathering potential. If the potential is getting too much, I issue output, okay? And the output that is issued by this cell is connected to the dendrites of other cells. So this output becomes input to other cells. That's basically it. That sounds like shooting electrical impulses around randomly, but it's not random. Why? Because the places where the axons of one cell are connected to the dendrites of other cells, these places are called synapses. Okay? And the synapses are not necessarily transmissive, that they let through everything. You can switch the synapses on and off, or even gradually. You can even let them turn the impulses around from positive to negative and vice versa. Okay? So the way that the whole interaction becomes a concert, something that has structure, is by the neurotransmitters in the synapses. Okay, so the program of this neural network is more or less stored in the synapses. There's an insulating synapse, there may be a transmissive synapse, or maybe a repelling synapse that turns a positive charge into a negative charge, and so on. Okay, so that's where the program actually sits. We can cast that into a very, very simple static model. The static model looks like this. We have inputs from x1, x2 to xt. So these are the dendrites of my cell. Okay? Every input has a weight, W1, W2, and so on up to WD, right? The input to the cell, or the potential in the cell, is just the weighted sum of the inputs weighted by the synaptic weights. Okay? And inside the cell, I have a threshold unit. If this potential is larger than a threshold theta, then my output is 1, otherwise it's 0. Okay, that's it. That's a static model. There is no dynamics over time. Okay, it's a vast simplification. But okay, that's a so-called perceptron. It's an invention of the 1960s. If you look carefully at it, it is nothing else but a linear classifier, right? You have a linear combination of inputs and an offset theta that you can shift. So the weight vector corresponds to a direction, to a rotation, to a normal vector of a separating hyperplane, and the theta just shifts this thing around. Okay? So what you can do with one such thing is you can solve linearly separable classification tasks with one neuron only. Okay? Of course, we're not talking about very complicated nonlinear things, but at least that works. The problem is you can only do linear things. And one of the first ideas in the 1960s was, if we don't want to deal with linear things only, if we want to get a little bit closer to the capabilities of the human brain, we need to have more than one unit. Okay? So why not stack them layer-wise, for instance? Okay? So we have inputs that are together connected to one hidden layer, then the hidden layer is maybe connected to another hidden layer, and so on, and finally you have an output layer. Okay? Wouldn't that be good? Yes, it would. But the problem was the training algorithm for the perceptron was always looking at misclassifications. So it always needed a reference input with a reference output to correct W and theta. If you have a hidden layer, then you actually have a reference input, but you have no reference output. You can only have the output in the very last layer, but you cannot say what should the reference output, the desired output of a hidden layer be. Okay? There's so many different things that could happen. So it was more or less impossible to transfer the perceptron learning algorithm to hidden layers. And Minsky and Papert, who were the popes of perceptrons, who wrote a well-acknowledged book in the end of the 1960s, said it doesn't work. And if it works, it will be too complicated. So it was a relatively unscientific conjecture they made, but that made the whole field to collapse and to be halted until the 1980s. And only in 1968, Rumelhart and McLennan came up with a trick that was really simple and allowed for training also hidden layers. And the cool trick, which is called backpropagation, which still exists today and is still used today, is not to have only reference outputs to adjust weights, but the trick is to compute an error signal, okay? And then you backpropagate the error signal. So you have an error signal also for the hidden layers. You don't have a reference input, but you can have an error signal. Basically, it just comes down to a nifty way of interpreting the chain rule. Do you know what the chain rule is? So if you have, if you compute the derivative of a compound function, take a little bit of mathematics in between. So if you have f of g of x, right? You compute the derivative of it. Then it's f prime of g of x times g prime of x. You heard about that? Yes, that's the chain rule. Okay, you need the chain rule in a very weird way to compute an error signal here, but it really works, and you can backpropagate the error signal, and then you can train also the weights between hidden layers, and that is the trick of backpropagation. Actually, it turned out that Rumelhart and McLennan were not the first who actually discovered it. It was already in Paul Werber's dissertation in 1974, and there is also works from Bryson, the 1960s, in a different context that somehow contained this. Okay, and suddenly neural networks were fashionable again. Okay, the interesting thing is they became fashionable again in the 1980s. And in the 1990s, support vector machines came along. In the 1980s, people were using neural networks with 1 or 2 hidden layers. And unfortunately, it did not work to have many more than those 2-3 hidden layers. And it was really difficult to train the networks properly. And at that time, there was not the computing capacity either for doing that. And support vector machines were then much easier to do and much easier to compute. And they more or less overruled neural networks in the mid of the 1990s. And just recently, people came up with new tricks that addressed the problems of the backpropagation algorithm. It mainly corresponds to the so-called vanishing gradient, which is a mathematical phenomenon that I don't have the time to explain in more detail. It was actually discovered by my boss Sepp Hochreiter at the beginning of the 1990s, but at that time everybody was already doing support vector machines and nobody was interested. Just 10 years ago, people discovered this again and started creating new methods for training neural networks. And there were some essential things that came together. First, you have much more computing capacity now. In the 1980s, there were PCs with single cores, or maybe some IBM mainframes, okay? So there was insufficient computing capacity. Now we have huge multi-core systems, and even more importantly, there are GPUs, graphical processing units. Why are graphical processing units important here? Because they're very, very cheap supercomputers. In fact, they're not general purpose, like a huge multi-core system, but they are optimized for basic matrix operations that appear when you do rendering in computer graphics, okay? And computing multi-layer perceptrons and training them largely consists of matrix operations. So you can very efficiently abuse GPUs to do neural network training. And you can have a GPU for 1,000 euros and you can have training speeds that would otherwise take several hundred cores on an HPC system, which costs millions of euros, probably. Okay, so that's amazing what you can do. That's the one thing. The second thing is large data sets. If you fit many parameters, you need large data sets to properly fit them. Okay, there is YouTube, for instance, where we are live today. You can have, there are so many large data sets that have been accumulated. This big data thing has been around for 10 years now. And third, new methods. Okay, improved training algorithms, improved backpropagation, improved activation functions that do not suffer from the vanishing gradient. And that's why now everybody's doing deep learning. Okay, so what is it? It's not one thing. It's a large class of strategies for training deep neural networks. By deep, I mean with many, many neurons, with many layers even. Okay? And if you do it right, then a deep learning can learn multiple levels of representations, of abstractions, in a fantastic way. Okay? It can be done supervised and unsupervised. The first approaches did something else. They stacked unsupervised layers and then had a shallow supervised learning in the end. That's no longer used. Okay, now you can have, with the new methods that are available, you can have really large deep neural networks and train them in a purely supervised fashion with more or less standard backpropagation. Okay, I think my time is over, right?
Yeah, more or less, yeah, you can use 5 minutes. No? But tomorrow.
Okay. No, I think I will stop here because there is another course as well. I'm right now at the point where it really gets interesting. Yeah. So I have motivated exactly deep learning to a point where I think we can very, very easily start from tomorrow. So I will start with this slide tomorrow and show you a lot of nice things. I will quickly go through, and you see nice pictures, right? Just to give you a glimpse so that you come back tomorrow. Maybe it was boring today, but tomorrow I think it will be really exciting. Okay? So I will finish this tomorrow. I think I will probably skip unsupervised machine learning because it's only a very, very quick overview, and then we will do practical workshop. I will show you some code, and I will let you work around a little bit by yourself. Okay, I'm not forcing anybody to join the practical session or to do things yourself. Maybe Osvaldo forces you.
Yeah, sure.
Yeah,
Sure.
but all those who want to take part of it, and I think you will have very easy successes. So it's finally really rewarding. So I suggest if you don't have R on your computer already, install it. Bring your laptop tomorrow. Go to the web page with the code. Maybe you can run already some parts, and there is also some instructions which packages you need to install, that you have everything on your computer that you need. And I will also show you some deep learning examples. Not as fancy as those, but at least that you have an idea what it looks like. Okay, so I hope that induces some curiosity for what comes tomorrow. Tomorrow it will be more practical and a little bit fancier as well. And I hope to see you again tomorrow. Thank you very much for your attention.
Thank you very much. For my students only, but for everybody. Esteban will include it somewhere, I suppose in the campus virtual or in the doctorate, some instructions to download and install R if necessary. Okay?
I think you have the instructions on the slides.
They are there, yes. Okay, I will.
Could you check?
I will show it
For
to
my
you.
students of project, I speak English. proyectos in
Oops,
bioinformática.
sorry.
We have the session now in 20 minutes, more or less, okay? And that will be a short session, 1 hour perhaps, to discuss one of the projects that Ulrich's team has prepared. Okay? And so all the people is invited to attend that, but it's not mandatory to attend. For the young people in the short course, it could be interesting to be there. But if you have classes, no problem. So see you in a few minutes, and thank you very much for coming.
Okay, I just wanted to show this to you. So here you have, this is what the page looks like. You can download the slides, and you have a zip file with R code examples and data sets. And in the zip file, you also find a README file. I will open it. And there you find instructions what to do. You even have 2 lines of source code with which you can install all the packages. Okay. And if you have any questions, drop me a line. It's exactly this URL that I displayed in the beginning. Maybe this is something that you can include or show somewhere that people know the link and don't have to write the link down anywhere.
Okay, thank you.
You're very welcome.
Very well.
No problem.